So in this video I will explain about the mechanism of hydration of alkenes, which is the conversion of 3,3-dimethyl-1-butene to 2,3-methyl to butanol. So in this video I will explain the first step. So the first step is the formation of carbocation by protonation of alkenes. So the carbon-carbon double bond in 3,3-dimethyl-1-butene contains a pi bond and a region of high electron density. So the pi electrons are most loosely held than the sigma electrons in a single bond. Therefore, this region will act as a nucleophile or a site that can donate electrons. So the H2SO4 will serve as the acid catalyst in this reaction. So within the H2SO4 molecule, the oxygen atoms are more electronegative than the hydrogen atoms, leading to partial negative charge on the oxygen atoms and partial positive charge on the hydrogen atoms. This electronegativity difference makes the H atoms electrophilic sites exhibiting a partial positive charge and attracting electrons from a nucleophile such as alkene. So the two pi electrons from the 3,3-dimethyl-1-butene carbon-carbon double bond will attack one of the H atom, which is this of the H2SO4. So the pi bond is broken as a result of this process. So the two sigma electrons between H and O atoms are pushed to the more electronegative O atom to form HSO4 negative ion. So the nucleophilic attack by the 3,3-dimethyl-1-butene pi bond result in the formation of a new sigma bond between the C atoms with more H atoms at 3,3-dimethyl-1-butene carbon-carbon double bond and the H atom from the H2SO4 breaking the pi bond in the process. So according to Markovnikov rule, the H atom from H2SO4 will add to the C atom at the carbon-carbon double bond with more H atoms. The application of Markovnikov's rule helps predict the major product form. The reduced selectivity is determined by the stability of the carbocation intermediate formed during the reaction. Thus, secondary carbocation is more stable than primary carbocation for this step, because the more alkyl substituted carbocation, which is the secondary carbocation, can better stabilize the positive charge through hyperconjugation and inductive effects. Now we move to the second step, which is the rearrangement. In the carbocation intermediate, a neighboring H atoms along with its bonding electrons migrates to the C atom carrying the positive charge. This results in forming a new carbocation at a more stable position. The hydride ion shifts from the C adjacent to the positively charged carbon to the carbon bearing the positive charge. So the hydride ion and the positive charge migration occurs simultaneously. And then after the 1,2 hydride shift, which is this, a more stable carbocation is formed. In this case, the positive charge is located at tertiary carbon, which is this, which is more stable than the previous secondary carbocation. So the rearrangement allows for a more substituted and therefore more stable carbocation, leading to a more efficient and selective reaction. So in the step 3, the formation of protonated alcohol by adding H2O. So water is the nucleophile in this reaction. So the water molecule will attack the positively charged carbocation, which is the tertiary carbocation formed in the previous step, using one of its lone pair. So by this, it will form a new carbon-oxygen bond, which is this, which also known as protonated alcohol. So the O atom bears a positive charge due to forming the new carbon-oxygen bond. So for the last step, the deprotonation of protonated alcohol. In this final step, a proton is abstracted from the positively charged oxygen, which forming the final product, 2,3-methyl-2-butanol. So the HSO4 negative is a base that attacks the proton on the positively charged O atom. So the HO, which is this, will break, and then the electron from the sigma bond will push toward to the O atom. Oh, I'm sorry. Here, the OH atom. They will break, and then the electron from the sigma bond will push toward the O, which is here. So the final product, which is the 2,3-methyl-2-butanol, will form after deprotonation. It is important to note that using H2SO4 as a catalyst is crucial in facilitating the protonation of the alkene and promoting the subsequent nucleophilic attack by water. The acid catalyst is regenerated at the end of the reaction, making it a catalytic process. Thank you.